This one is the second one is the easiest because you can actually just plug it straight into the equation. So you had to research your favorite car, and what is MSRP? Manufacturer suggested retail price. That's exactly right. So what's our suggested retail price going to be? $25,000? Okay, that's fine. So you have a $25,000 car. What interest rate are we going to use? 5%? Does that sound good? Is that around what you found when you did you actually look? Did you find?
I asked my parents.
Yeah. What? 3 point. Yeah. You can also look at commercial. 3.6. Yeah.
Parents, because
yeah.
Just bought a new car.
Yeah.
Around that.
Around 5.
2.9.
2.9. Let's say. How about 3? Let's say 3. Car ones tend to be a little lower because it's a shorter loan. Usually lower interest on shorter loans because you're paying it back faster. So let's say it's 3%, $25,000. So in this case, is the interest rate working for or against you?
Okay.
Against you. So does it actually fit this formula really nicely? It fits it perfectly, doesn't it? What does A represent? What is A called? The amount you have to pay. That's correct. The amount you're going to be paying. The amortized amount. The amount you're going to regularly pay. So the amount. So we're solving for A. What do we? What's our p-value? 25,000. That's correct. Okay. So what about this I thing and this R and this N? Well, we can do R. What's R?
It's I.
Oh, that's I. Remember, that's the typo I made. Yeah, great. Yeah, nice. That is supposed to be I. That is correct. So in this case, what did I say I was equal to? R over N. So the interest rate divided by the frequency per year, right? 0.03 over what? So it's 1 plus 0.03 over 12 raised to the what power?
12 times however many years.
12 times. I didn't specify this. I mean, this is something you'd have to decide on your own. For a car, you have to decide the length, right?
They have limits. Like how many years you have to pay within this.
Well, let's 5. You have to pick an amount of time, right?
5 years.
So N is going to be the number of payments in this case. N is the number. I think I specified that in this, right?
Yeah.
N is the total number of payments. This is slightly different. I know it's poor to overlap, but that's just how it is. Sorry. In this case, if it was 5 years and you're paying monthly, how many payments are you making? So 60 payments, and it's going to be 0.03 over 12, and then it's going to be 1 plus 0.03 over 12 to the minus. Now, what's the way you're not supposed to plug this into your calculator? Please don't do that all at once. What should you do first?
Store them.
Or 1 plus 0.03 over 12 to the 60th. That's what I would do. You can. Yes, you can. Absolutely. That's fine. Yeah? Yeah, sure. Let's do it. I'll do it in 2 ways. So 1 plus 0.03 divided by 12. I'm going to raise that to the 60th power. And I press enter. It's that nice terrible decimal. You STO, it's in the bottom left. STO, and then you pick a value. I'm going to say A. So if I just alpha A'd that, so it's going to be 25,000 times 0.03 over 12. And that's actually a really good thing to do because you have to write 0.03 over 12 again. You're absolutely right. That's a good thing to do. Times A over A minus 1. So if we do out, 25,000 times 0.03 divided by 12 times what? A. I'm going to hit enter on that, and then I'm going to divide it by A minus what? 1, I think. So what's your monthly payment? Now, does that seem reasonable? Yeah, on a $25,000 car, 5 years, that's about reasonable. So so now that you know what your monthly payment is right here, what might it be interesting to determine?
How many money you pay overall?
Yeah, how much you paying over the life of the loan. So that's your monthly payment. So how do I find how much I pay total?
Times 12 times 18.
Times what? Times 60, right? 60, right? So how much do I end up paying?
You end up paying like 26,000.
Now, overall, from what we've seen in the past, when you see that, so now what can you calculate? So this is what you've paid overall.
Greater than the initial amount.
So this is a simplification. This is total paid. Total paid. So one way to think about it is how much interest have you paid? $1,953 and...
47.
Now that's actually not super accurate, but it's a minimum of that much interest. Why is that actually less than how much you've actually paid? Think about it this way. If you just put money into a bank, what happens to when you put money into a bank? It earns interest, right? So this amount of money, $1,953, was it all paid at the same time? No, it was paid over, like certain slices of each monthly payment was just interest, right? So that part that was interest, if you think about it that way, it grows a little bit. But that's the best way to think about it right here, the least complicated way to think about it. So from what we've seen, that seems like maybe a lot of money, but compared, what did we look at? Do you remember before break we looked at buying what in class? Do you remember? Buying a house, right? And over the course of the life of the loan of a house, so this is $2,000, right? So you can think of this as you paid $2,000 on a $25,000 loan. That's like 4%. That's what's that going to be? 8%. You paid 8% the initial value in interest, right? What was it for a house? Or what? No, it was even more than that. It was like double, right? You paid almost 100% the value of the house in interest by the time you finished paying off the house. And what we found is that that's not super abnormal. Okay, so is this? Let's just do the reality check. Is that a realistic amount of money that you've seen on a $25,000 car for 5 years? Yeah, absolutely. $449 just for the car payments.
Wait, so is that a
monthly payment?
So you divide by 12?
No, that is how much you pay each month. It tells you directly how much you pay each month. Okay, so which one do you want to do next? 3 or 1?
1.
Nope. 3.
So why you have that?
Well, you know, I have to direct it. We're going to spend a long time on number 1. If I put $10 into my account every week and the account earned 4% yearly interest, how much money would I have in the account after 10 years? Now keep in mind, we have this formula. Does this fit the formula?
No.
It doesn't?
No. When I plugged it in.
Why not? Let's think about it. So what does I represent? The interest rate over
Time.
over number of times per year, right? Okay, great. What does this the new thing here I think is this $10 right here. Where does that go into the formula? That is A, right? So that is, say, let's build this so far. So we know A, so that's going to be 10 equals, do we know how much? No, we don't. What is I going to be? Or we think it's going to be. What? Over what? 52. How many times per year? It's weekly, right? 1 plus 0.04 over 52. And it's 10 years, right? So it's 520. 1 plus 0.04 over 52 to the what? 520 minus. Did anybody actually try to do this right here? Did it work? What'd you get for a p-value? What? Can you speak loudly? Point what? 0.1? Well, what would be a quick way to do a reality check on that to see if it would be even close to reality? Not dividing. Well, we're putting $10 in the account every week, right? If we don't account for interest, what could we do? 10 times 52 times 10 years, right? So what does that become? That's 5200. So that's how much base we're putting total in deposits, but what doesn't that account for? It doesn't account for interest, right? Is it possible for $5,000 to turn into $12,000 in 10 years? Reasonably in your head, is that a reasonable thing? As opposed to turning into millions of dollars? Yes. It seems semi-reasonable, I think. I think it's semi-reasonable. If you actually do this out on your calculator, yes or no? Yeah, they're pretty similar. They're pretty similar. So why is the amount going up right here in these little humps right here? What? Because what? Interest on the loan, right? So it's increasing the amount you owe. But in this case, it's increasing the amount of money you have in the account. You see what I'm saying right here? Okay, so instead of thinking about this as one account, you can think about this as different accounts for different amounts of time. The first payment is in there for how long? Let's say this was a 5-year loan. So let's say 60 months right here. How long is that first payment in there for? 60 months. How long is the next payment in there for? 59. The next one's in there for? So could you think of it as 60 different accounts that you add together? Yeah, you could think of it as 60 different accounts that you add together. Now, that makes sense because if I put $100 in an account earning 5% interest, and I put $100 into an account earning 5% interest, is that this for 2 years? Is that the same thing as putting $200 into an account at 5% for 2 years? Overall? If I put $100 into an account earning 5% interest for 2 years, and I put the same amount of money in a different account for the same amount of time, do I overall end up with the same amount of money as if I did $200 in the same account? Yeah, you do. It doesn't matter where the amount of money is. It doesn't compound more because it's in the same place. Does this make sense, everybody? So when you're making these monthly payments, you can think of it as separate. How many separate payments are you making? Just how many? 60 payments. Now, do we want to write out 60 equations? No, so let's make this a little simple. Let's do a simpler one and let's see if we can find out. Type that into your calculator, use the store command. It should be more than how much money? It should be more than what? It should be more than 600. Yes. Term to the second term. No. Well, yeah. No, you multiply by 2. And you multiply by? And you multiply by? Multiply by? Multiply by? Do you agree? Do you agree with that?
Yeah.
Yeah? Okay, good. So it's the same. It's a geometric series. If to get to the next term, you always multiply by the same thing. So how many different geometric series are there?
1.
5 of them. Yeah, there's 6 of them. No. How many different numbers could there be? Instead of 2, you could do 10, right? You could pick a different number for this. Would it still be a geometric series?
Yeah.
Yes. So there are an infinite number. Remember, there's only 0 of something, 1 of something, or many. many, 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 many. Okay, so we're trying to figure out, is there any way to combine these? Is there any way to put them together?
They can.
No. The additions, there's nothing in logarithm length, and also this doesn't, we don't know what it equals. We could say it equals s. So let's say it equals s. So s is equal to some first term. And instead of this, let's call that the ratio. Let's call that r. So if the first term is a, can someone tell me what the second term is if the ratio is r? A times r. What's the next one going to be?
That's R squared.
A times r. A times r to the 4th, and 8 plus a times 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, a times r to the. So this would be true if a was 2 and r was 2 as well. I'm just generalizing it, okay? A could be any starting value and r could be any number. We're doing it in general. This is where random math maneuvers come in handy. So I'm going to take this statement. If I multiply the left side by something and I multiply the right side by the same thing, is it still a true statement? Yeah. If I multiply the left side by 10 and the right side by 10, is it still a true statement? So I'm going to multiply both sides by r. So I'm going to make it rs. So if I multiply everything by r, what does this become? A to the plus a to the r squared plus a to the r 4, a to the r to the 5th plus a r to the 6th. Are these both true statements? If I multiply the left side by a pony and the right side by a pony, I still have a true statement. Are we okay with this?
Yep.
You don't like my ponies? Are we allowed to subtract equations from each other?
Yeah.
Yeah, sure, why not? So if I subtract these two equations, the left becomes s minus r times s. Right? What happens to the right side? What happens to the right side? That cancels, that cancels, that cancels, that cancels, this cancels. What are you left with? No, a minus. We're subtracting what? ar to the 6th, right? No, we're originally trying to find the sum. We want that s value, right? We want to isolate what? We want to isolate s. So what do we factor out of the left? S.
R minus 1 minus 1.
And what can we factor out of the right? 1 minus So what does S equal? A times 1 minus r to the 6th over
Over,
over what?
1 minus r.
1 minus r. So in this case, remember this represents 6 terms, right? How many terms could you go to?
And
You go infinite, right? See all these cancellations right here? How long could this be? As long as you want, right? How long would this be? Really long, right? But how many things would cancel? All of them except for
the last one
the
is
first and the last. So does it matter how long this is? No, it doesn't. It doesn't, right? Totally doesn't. Totally doesn't. So the general, I'm going to generalize this further. I picked 6 just so you could have a finite number. The generalization of this is as follows. If you have S equals A plus A times R plus AR plus AR cubed, and you go all the way to that right there. You go all the way to the AR to the n minus 1. S is going to be equal to A times, remember we had, how many terms did we have before here? We had A with this to the 0 power all the way to the 5th. So in this case, n minus 1 was 5, but it turned out that the formula you needed what? 6. So if n minus 1 is 5, what is 6? Is n. 1 greater, right? So what does the formula actually become? 1 minus r to the over 1 minus r. How many terms do you see there? I just see one thing you have to multiply out. Does it matter how many initial additions you have to make? Okay, how many terms did we have in our initial one right here? 1, 2, 3, 4, 5, 6, right? What does this formula allow us to do? Yeah, and how many terms do we actually need to add together? Well, we don't add anything together, we just actually plug it into this formula. The sum of the first n minus 1 terms in a geometric series is that right there. Is that right there. And the reason I give this to you is, what is this right here? That's a geometric series. Here's the key. What's the r value? What do you multiply each term by to get the next one? 1 plus 0.05 over 12. To get, this is the first term, you multiply by 1 plus 0.05 over 12, you multiply by 1 plus 0.05 over 12, you multiply by the same thing, right? You multiply by the same thing, you multiply by the same thing, right? Okay, so let's go back to that first question there. So what was that first question? $150,000, right? You want $150,000. And what's the interest rate we get? Can you just look? 5%. And you want 18 years, right? 5%. 18 years. Is that correct, everybody? So when we add all these things together, we want to get $150,000. So what is our S value? What? $150,000. So in this case, what are we solving for? We're solving $150,000 equals, do we know what our A value is in this case? No, we don't know what our A value is in this case. 1 minus, what's our R value? 0.05, not 5. What happens if you put in 5? Kaboom! You're earning a lot of interest. To the what power?
Power of...
What n value is it? How many terms? 18 times what? Yes. Very good. Very good. We can save it as R. So it's going to be 1 plus 0.05 divided by 12. And we'll save that as alpha R. So if we actually want to do this out, what is A going to? So 1 minus, so maybe we should do this now right here. 1 minus R to the 217th power. 1 minus alpha R to the 217th power. Okay? And what's it over? 1 minus, and that better be negative, right? Why is it really important that it's negative? It better be positive, right? Alpha R So then what's on the left here? 150,000.
Divided by that one.
Yep. So 150,000.
Divided by 100.
And what do you end up with? 400 and... that right there. Yay.
Lower than the next one.
Exactly. Now, does that match? What was our first thing we checked in? We checked that the absolute max if we made zero interest was like $694. This tells us that if we put away $426 every month, we're going to end up with $150,000. We need to figure out how much interest we actually earn here, or an approximation. So what should we multiply that by? 200 and what? 16 payments, right? Cool. You actually put away payments equaling $92,000, but how much you end up in the account? 150. It's pretty cool. It's pretty neat.
Hey, wait, Mr. Seaman?
Yes.